Dear students, do you want to get into the fascinating world of physics? Please see this video and also subscribe to this channel. Dear students, in this video we are going to study about the wave optics, Huygens principle proof for laws of reflection and refraction using Huygens principle.
Dear students, in this video we are going to study about the wave nature of light. Light is a transverse electromagnetic wave. The wave nature of light was first demonstrated through experiments like interference and diffraction. The transverse nature of light is demonstrated in polarization effect, and like all electromagnetic waves, light can also travel through vacuum. Now let us see about this wave optics. This wave optics deals with the wave characteristics of light. Even the law of reflection and refraction are proved only with the help of wave optics. Though light propagates as a wave, its direction of propagation is still represented as a ray, like this. So a good example for wave propagation is the spreading of circular ripples on the surface of still water from a point where a stone is dropped. That is like this. So if you drop a stone here, you can observe these ripples formed, that is as their circular waveforms. The molecules or particles of water at a point are moving only up and down, that is, they oscillate when a ripple passes through that point. All these particles are the circular ripple, that is, all the particles on that circular ripple will be in same phase of vibration as they are all at the same distance from the center. The ripple represents a wavefront as shown in this diagram. So here, and a wavefront. What is a wavefront? A wavefront is the locus of points which are in same state or phase of vibration. This you should remember and write this as the definition for wavefront. When a wave propagates, it is treated as the propagation of wavefront. The wavefront is always perpendicular to the direction of the propagation of the wave. As the direction of ray is in the direction of propagation of the wavefront is always perpendicular to the ray as shown here. You can see the plane wavefronts, and it will be perpendicular to the direction of propagation. The shape of a wavefront observed at a point depends on the shape of the source and also the distance at which the source is located. So a point source located at a finite distance gives spherical wavefronts. An extended or line source at finite distance gives cylindrical wavefronts. So there are three types. The third one is any source that is located at infinity gives a plane wavefront. So you can see this in this diagram. A point source, a line source, and a source at infinity. So they will give rise to spherical wavefronts, cylindrical wavefronts, and plane wavefronts. Now let us see what is Huygens principle. This will be asked in 5 marks. Huygens principle. And you can also expect the same in 2 marks, state Huygens principle. So Huygens principle is basically a geometrical construction which gives the shape of a wavefront. At any time, if you know its shape at t equals 0, that is at any instant at the starting time, if you know the shape of the wavefront, you can predict what will be the shape of the wavefront after a time t. So according to this Huygens principle, each point on the wavefront behaves as the source of secondary wavelets spreading out in all directions with the speed of the wave. These are called as secondary wavelets. The envelope to all these wavelets gives the position and shape of the new wavefront at a later time. Thus Huygens principle explains the propagation of a wavefront. The propagation of a spherical and plane wavefront can be explained using Huygens principle. For that, let AB be the wavefront at a time t equal to 0, and according to Huygens principle, every point on AB acts as a source of secondary wavelet which travels with the speed of a wave, which is equal to c, the speed of light. To find the position of a wavefront after a time t, circles of radius equal to ct are drawn with points p, q, r, etc. as the centers on AB. The forward envelope or the tangent a dash b dash of the small circles is the new wavefront at that instant. The wavefront a dash b dash will be a spherical wavefront from the point object which is at a finite distance as shown. And it will be a plane wavefront if the source of light is at a larger distance as shown in this diagram. So you will get a spherical wavefront when the point source is finite distance. You will get a plane wavefront like this if the source is at a large distance. Then there is one shortcoming in the above Huygens construction for propagation of a wavefront. It could not explain the absence of backward wave, which also arises in the above construction. According to electromagnetic wave theory, the backward wave is ruled out inherently, and however, Huygens principle is a good diagrammatic construction which explains the propagation of the wavefront.
According to Huygens principle, each point on the wavefront behaves as the source of secondary wavelets, spreading out in all directions with the speed of the wave. These are called as secondary wavelets. The envelope to all these wavelets gives the position and shape of the new wavefront at a later time.
Now let us study about the proof for the laws of reflection and refraction using Huygens principle. The first case, let us study about the laws of reflection. Let us consider a parallel beam of light is incident on a reflecting plane surface, such as a plane mirror x1, as shown in 7.4, this one. The incident wavefront is AB and the reflected wavefront is A dash B dash, and these wavefronts are perpendicular to the incident rays L, M and reflected rays L dash and M dash respectively. By the time point A of the incident wavefront touches the reflecting surface, the point B is it to travel a distance BB dash to touch the reflecting surface at B dash. When the point B touches the reflecting surface at B dash, the point A would have reached A dash. And this is applicable to all the points on the wavefront. Thus the reflected wavefront A dash B dash emanates as a plane wavefront. The two normals N and N dash are considered at the points where the rays L and M fall on the reflecting surface. As reflection happens in the same medium, the speed of light is same before and after reflection. The time taken for the light to travel from B to B dash and A to A dash are the same. Thus the distance BB dash is equal to the distance AA dash. So AA dash will be equal to BB dash. And according to the laws of reflection, the incident rays, the reflected rays and the normal are in the same plane. And also the angle of incidence I will be equal to the angle of reflection. So for the two right angle triangles, the triangle ABB dash and triangle B dash A dash A, the two right angles, angle B and angle A dash are equal, as angle B and angle A dash are equal to 90 degrees. The two sides A dash and BB dash are equal. That means A dash is equal to BB dash. The side AB dash is common, thus the two triangles are congruent. As per the property of congruency, the two angles, angle BAB dash and angle A dash B dash A must also be equal. Therefore, angle of incidence I should be equal to angle of reflection R. So the laws of reflection are proved. Next we will study about the proof for the laws of refraction using the same Huygens principle. For that, let us consider a parallel beam of light is incident on a refracting plane surface xy such as a glass, as shown in figure 7.5 here. So in this case, the incident wavefront AB is in rarer medium 1 and the refracted wavefront A dash B dash is in denser medium 2. These two wavefronts are perpendicular to the incident rays LM and refracted rays L dash M dash respectively. And by the time the point A of the incident wavefront touches the refracting surface, the point B is said to travel a distance BB dash to touch the refracting surface at B dash. When the point B touches the refracting surface at B dash, the point A would have reached A dash in the other medium. And this is applicable for all the points on the wavefront. Thus, the refractive wavefront A dash B dash emanates as a plane wavefront, like this. The two normals N and N dash are considered the points where the rays L and M fall on the refracting surface. As refraction happens from rarer medium to denser medium, the speed of light is v1 and v2 before and after refraction, and v1 is greater than v2. But the time taken t for the ray to travel from B to B dash is the same as the time taken for the ray to travel from A to A dash. So that means t will be equal to A dash by v2, or bb dash by A dash will be equal to v1 by v2. And by the laws of refraction, the incident rays, the refracted rays, and the normal are in the same plane, and the angle of incidence I will be equal to the angle of refraction. And for the two right angle triangles ABB dash and AAA dash B dash, sin I by sin R will be equal to C by V2 by C by V1, where C is the speed of light in vacuum. The ratio C by V is a constant which is called as the refractive index of the medium. The refractive index of a medium is C by V1 will be equal to N1, that's for the first medium, and C by V2 equal to N2 for the second medium. And in the ratio form you can write like this: sin A by sin R equal to N2 by N1. And in product form this can be written as N1 sin I equal to N2 sin R. Thus the laws of refraction are also proved. So the speed of light is inversely proportional to the refractive index of the medium, that is V proportional to 1 by N, and also directly proportional to the wavelength of light, that is V proportional to lambda. And the laws of refraction can be proved for wavefronts which are traveling from denser to rarer medium. We can prove like this. And lambda 1 by lambda 2 equal to N2 by N1. So this is how the process of reflection and refraction are explained on the basis of Huygens principle.
For centuries, we've thought of light as a straight-line beam, but that intuitive ray is actually a macroscopic illusion, hiding a complex reality of three-dimensional undulating waves. In the 17th century, early physicists like René Descartes modeled light strictly as a stream of perfectly elastic, massless particles. They called them corpuscles, traveling through space like tiny, high-speed billiard balls. That particle model worked for basic reflections, but it failed completely to explain how two overlapping beams of light could cancel each other out in an interference pattern. To solve this, Christian Huygens proposed that light wasn't a particle at all, but a longitudinal mechanical wave, propagating through a physical medium. James Clerk Maxwell later refined this. He proved that light doesn't require a physical medium to travel. Instead, it is a transverse electromagnetic wave, capable of propagating directly through the vacuum of space. Later work by Max Planck and Albert Einstein showed that while light interacts with matter as discrete packets of energy, photons, its actual journey through space remains strictly wave-like. To mathematically predict how light moves, reflects, and bends around objects, we have to set the particle model aside. We have to analyze it using the rules of wave optics. To understand wave propagation, we first need to look at how energy travels through a medium without taking the actual particles with it. Look at these concentric ripples spreading across a pond. The water molecules aren't moving horizontally away from the center. They are only oscillating up and down in place, but they do so in a highly synchronized pattern. We call the specific state of vibration of any particle at a given moment its phase. If you freeze time, every water molecule exactly at the crest of a single ripple shares the exact same phase. A continuous locus of all points in a medium that share the exact same state of phase is called a wavefront. When we measure the speed of light, we are not clocking the velocity of an individual particle shooting through a void. We are tracking the forward propagation of these continuous wavefronts. The geometric shape of a wavefront is dictated entirely by the physical shape of the light source and our distance from it. This animation shows a point source at a close distance. The energy radiates outward uniformly, creating spherical wavefronts. If we change the emitter to an extended vertical line, the geometry stretches. The expanding energy now forms nested cylindrical wavefronts. Watch what happens as we move incredibly far away from the source, say the distance between Earth and a distant star. The vast radius flattens the curvature until the waves arrive as parallel flat sheets. We call these plane wavefronts. Now we can reintroduce the idea of a light ray. In wave optics, a ray is not a physical object. It is strictly a geometric vector arrow indicating the direction the wave is traveling. Because of this, there is an absolute geometric rule. The light ray is always precisely perpendicular to the wavefront. By knowing the exact shape and orientation of a wavefront, we can map the exact trajectory of light without relying on corpuscular physics. If we freeze a wavefront in time, how do we mathematically calculate its exact shape and position 1 microsecond later? This diagram models Huygens' principle. We begin with a known primary wavefront at time 0, which we'll label AB. Huygens' core axiom states that every single point on this initial wavefront acts as a microscopic source for new secondary wavelets. Let's isolate 3 points, P, Q, and R. These secondary wavelets spread out in all directions at the speed of the wave, the speed of light, denoted by c.
After a given time t, the radius of each wavelet is exactly c times t. To find the primary wavefront's new position after time t, we draw a tangent line that perfectly touches the forward edge of all these expanding wavelets. This gives us our new wavefront, A', B'. Huygens' principle gives us a purely geometric mechanism to propagate light forward step by step, allowing us to solve complex optical phenomena. Let's apply this construction to reflection. Here is a plane wavefront, AB, approaching a flat mirror, surface xy, at an angle of incidence I. We pause the clock at the exact moment the bottom edge of the wavefront, point A, strikes the mirror. Notice that the top edge, point B, is still traveling through the air. It takes a specific amount of time, t, for point B to cover the remaining distance to reach the mirror at a new location, point B'. That distance is its velocity times time. Track point A. During that exact same time t, point A acts as a secondary source, emitting a reflected wavelet back up into the air. Because both points are moving through the exact same medium, their velocity is identical. That means the radius of point A's expanding wavelet is perfectly equal to the distance point B just traveled. Length AA' equals BB'. We construct the new reflected wavefront by drawing the tangent envelope from point B' over to the outer edge of A's wavelet. This process forms 2 distinct right-angled triangles sitting on the mirror surface. These triangles share a common hypotenuse. They both contain 90-degree angles, and we already proved they have one identical side length. By the rules of geometry, these 2 triangles are perfectly congruent. Because they are congruent, their internal angles must match. The angle of incidence strictly must equal the angle of reflection. The macroscopic law you learned in grade school is just a side effect of a wave maintaining constant speed. We can run this same geometric proof for refraction. Here is our wavefront passing from a rare medium, like air, into a denser medium, like glass. The defining physical condition for refraction is that light travels slower in a denser medium. Velocity 1 in the air is greater than velocity 2 in the glass. Watch the moment point A breaches the dense glass. Point B remains up in the faster rare medium. In a set amount of time, point B races through the fast medium to reach the boundary, covering a long distance equal to velocity 1 times time. Contrast that with point A. It generates a wavelet inside the dense medium, but because it is forced to travel slower, the wavelet's radius, velocity 2 times time, is significantly smaller. Drawing our tangent line from B' to the edge of A's much smaller wavelet forces the entire wavefront to physically tilt. To measure this tilt, we isolate the 2 triangles formed across the boundary. Calculating the sine of the angle of incidence and the sine of the angle of refraction gives us these 2 equations. When we divide the incidence equation by the refraction equation, the shared hypotenuse and the time variables cancel out completely. We are left only with the ratio of their respective velocities. A specific medium's refractive index is calculated as the ratio of the speed of light in a vacuum to its speed in that medium. By substituting the velocities for their respective refractive indices, we arrive at the foundational formula for optics, Snell's law. Light doesn't bend because particles are being pulled by the surface of the glass. Instead, it bends as a strictly unavoidable mathematical consequence of a wave slowing down asymmetrically across a boundary.